Hey guys, welcome again in Eng-Man YouTube channel. So today we are going to have another episode of WellFlo, and in this WellFlo video I'm going to show you a practical case of a well. Actually it's about a water source well. So sometimes we use or we work over or even we drill a well for the objective of providing supply water, makeup water for our water flood or water injection operation. So I'm going to prepare or I want to model a water source well. And I will equip the well with electrical submersible pump. And of course, I will do the modeling using WellFlo software. Okay, so let's go ahead. So this is the dashboard. It's not a final model. So actually, I already have a sort of almost done model, but I think I'm just going, I will check each of the value and maybe I will do some corrections to the model. Okay, so it's a practical case. You can follow me if you also want to know about well modeling or specifically water source well modeling. Okay, so here we are in the dashboard, model navigator, and then initialization, general data. Okay, company Eng-Man, well, number X, field YT, okay, YouTube, and analyst Eng-Man, whatever you can input these cells whatever you want, and then well type and flow type. Of course, it's producer, it's a water well, and we will use electrical submersible pump. Of course, the flow type will be through the tubing, fluid type black oil, and the well orientation it's vertical. Both vertical and directional or deviated well will be modeled by this vertical mode. Forward and flow correlations, you can start with you know the traditional flow correlation like Hagedorn Brown, Bex and Brill, Duns and Ross. But if you already have sort of study or statistical study to determine the best the best correlation to use, you can also use that. Actually, the best thing is of course by conducting tuning or matching, but in this in this particular example it's a new well, so we don't have pressure or gradient survey data that we can match on. Okay, so I'm just going to use the traditional or the basic flow correlation, Hagedorn and Brown in this case. Okay, and then reference depth, well type onshore, and zero depth at wellhead. Okay, so we have the distance or the location of the Kelly bushing, where the Kelly bushing is, and then the Braden head or the wellhead, and the KB distance to Kelly bushing minus distance to the wellhead or Braden head, KB minus BH. I use that and do some adjustment. Okay, basically we are defining or we are setting the zero depth in this selection. Okay, so I'm going to measure all my distance based on the wellhead position. Okay, so please be careful because depending on how big, how large, how great the distance to the Kelly bushing or rotary table, it can make some errors in your calculation. Okay, so I will be a little bit careful here. I use wellhead. Okay, fluid parameters. PVT calculation method, black oil, and it's actually water well, so all these numerical values don't have significant meaning, okay? But the most important thing is here, water salinity. In this case, 10,000 ppm, and here, the water gravity will be calculated automatically. And then gas specific gravity, if you have gas flow, 0.7, it's a typical value. And if you want to generate the PVT information, you can expand this little window and then you can just click on calculate button here. Okay, but of course all these calculated values will be used during the simulation, during the modeling. Okay, so I'm going to click on apply, forward, and then reservoir. Okay, so this is very important section. Wait a minute. Okay, so yep, go to general, the name of our reservoir, I call this sand, and the pressure in PSIG, it's 800 PSIG, the temperature 186 degrees Fahrenheit, and the mid perf depth, the location of the middle of perforation. Let me check my correct value first. So it's going to be at 3,317. Okay. And the permeability, let me check my value again. The permeability for my reservoir, it's 79. Okay, it's 79 millidarcies. All right, and then the thickness in TVD, the thickness of my reservoir, it's 53 feet, wellbore radius 0.35, and water cut 100%. It's a water source well. And here you can see the productivity index will be calculated. And then for the IPR modeling, I'm going to use Vogel equation with Vogel coefficient of 0.2. And to have a better calculation, I use calculated skin in this model. Okay, and drainage area geometry, I'm going to use 250 meters. It's a typical value, and drainage shape is circular shape. And then IPR, so it's like this. We have the absolute open flow, 4,398.99. And skin, let's see the skin modeling. Completion type, it's a cased hole well. And the nearest measured formation distance from my top perforation. Let me check my value first. So it's about 3 feet. Okay, so the top reservoir, the distance from the top reservoir to my top perforation, this is the nearest distance, it's 3 foot. Okay, and then vertical permeability, I'm going to use 10% of the horizontal permeability, so it will be 7.9. And then open interval, I will perforate my well 40 feet long. Okay, so the perforation interval will be 40 feet long. So the calculated limited entry skin, it's 1.3, quite small. And then the deviation skin, for deviation skin, let me check my value first. So I will use my deviation skin because it's, okay, so it's a directional well, and the deviation is 27. Okay, so I'm going to have a small negative skin. Okay, I like that. I like negative skin. It improves my productivity, although not very significantly. And then perforation. We also want to calculate the perforation skin, the skin due to perforation. So the perforation diameter will be 0.26 inches. And crash zone, I don't have reference data for that, so I will uncheck that. Shot penetration 1 feet, 1 foot, and shot density 6 shot per foot, and shot facing 60 degrees usually, and flow shape factor, you can use lock, Egan, and then tarik, okay, and muscat. The template, the format is lock. Okay, so we can use that lock. So the perforation skin, lock will give me the lowest skin, lowest positive skin. So let me use this value. So the final productivity index is 9.3 or 9.4 stock tank barrel per day per PSI, which leads to absolute open flow or maximum flow rate of 5,400, and the final total Darcy skin is 2.9, which is good. So let's check the IPR. So it's the new IPR. Okay, so I will click on apply and deviation. Okay, yep. So it's a correct deviation already, 27. The inclination, yeah, you can input, of course, your trajectory, measured depth versus true vertical depth. In this case, I already prepared that, and yes. So this is the trajectory of my well. And then the equipment, okay, for the tubing, I will call it tubing. Okay, so I will locate the end of the tubing at 3,250 feet, and the external diameter is 2.875. It's 278 inches of tubing with the internal diameter of 2.441. So it's a typical tubing to be used in this configuration, in this well configuration. Okay, and absolute roughness, typical value 0.0012. Flow configuration, of course, through tubing, no drift diameter. And then casing. So I will call my casing as casing. So the end of measured depth for my casing is at 3,400 with the final diameter. Okay, it's 7 inches and the internal diameter is 6.1. Internal diameter of casing is important because, of course, don't forget we will use electrical submersible pump in this case. Okay, so far so good, no restriction. But if you have like valve, you can input that or some restrictions. But I will delete that. Trace points if you have. And temperature model. Okay, I will just use calculated surface surrounding temperature. The surface temperature 86 degrees Fahrenheit. If you're wondering what is the centigrade value, you can also check the Celsius value. It's 30 degrees Celsius. And yep, it will be calculated. So this is the, at this depth, measured depth, it will be calculated. So it's just like that. It's very easy. And ESP data. Okay, so currently in this model file, I have DN 3100 radar pump, okay, with number of stages 160, pump wear factor 1, okay. But yeah, this is the range of the performance, okay, around 2000, the minimum flow rate up to 3900, okay. So this is the motor model, okay, 375, nameplate rating, operating rating for the motor, and pump environment, okay. This is the location of the pump location, and maximum OD, minimum equipment OD, operating frequency 60 hertz, upstream temperature 90, pump name radar 3100, and so on and so forth. But I actually want to use another pump. So let me delete this first and click on this one. Okay, and select catalog data. expand the radar, expand this window. I already input my this this pump, DN to 400, okay, with OD of 4 inches and shaft limit at 60 hertz and housing limit. I already input all the data for this specific pump on the WellFlo, so I can just use that. So I will use DN 2400 REDA in this case, and the minimum flow rate is 1500, maximum flow rate 3200. So if you want to operate this well, make sure you don't operate below 1500 or greater than 3200 because it will lead to down thrust or up thrust. Okay, so far so good. And let me check my another sorry, another data for ESP design to know how much or how many stages I will have in this specific case. Okay, so I'm going to use 60 stages. Okay, and then motor model. Okay, for the time being, I only have motor of this one. Okay, 90 horsepower. Okay, and then motor model. Okay, radar. Yeah, I will use this one, 375 SX series. Okay, and I think that's all. Later, I'm going to also dig in more deeply in another calculation for the ESP design so we can move forward, apply, and go to analysis. Okay, so, oh, wait a minute, go to flow curves, operating point, and yeah, analysis type operating point. We want to know the operating point, of course, and then expand this one. Okay, and then top note, the wellhead pressure. Let's go to PSIG. Yeah, 125, the wellhead pressure. And then the bottom note, this one at this location, the reservoir. And solution note, let's say I want to know at the, let's see. Okay, so yeah, I changed my pump name, apply, analysis. Okay. Okay, so for now, solution node cannot be at the perforation depth. Okay, you see I move everywhere, but I cannot find it. So the solution node, if you have ESP, it will be at the location of the ESP, not on the bottom hole or the perforation or the mid perf location. Okay, so you just to know you just need to know that. So the solution node will be at the pump itself. This is the location, the pump setting depth, 3250, which is actually the the end of the tubing, the depth of the end of the tubing. And okay, and set range. Let's see, percent AOF from 1 to 99. Auto range. Click on OK, and then apply, and then calculate. flow curves. That's the main thing that we want to know. Okay, so with 60 stage, if I'm not mistaken, with 60 stage, I will achieve flow rate of 1300. It's below pump minimum, so I will have downthrust issue. But yeah, first thing first, you can see the IPR and you can see also the outflow or the vertical lift performance. I will have liquid rate of 1300, the same with water rate, don't have gas and don't have oil for this case. Okay, so this is the pressure, operating pressure. And this is the, yeah, this is the send phase pressure, 672. And this is the operating pressure or the pressure at solution node. Okay, the pressure at the pump depth. And this is the pressure at the bottom hole, at the perforation depth. Okay, and ESP performance at, currently we are here below the minimum flow rate. Okay, and then this is the head, and okay, you can see also the legend. Okay, head here and horsepower there. Okay, so this is the line for the power, and this is the line for the head, and of course this is the flow curve. Wheelbar equipment, okay, starting from this pressure, okay, the reservoir pressure, and then of course this is the bottom hole flowing pressure, and this is the pump setting or the pump intake pressure, 646, and this is the pump outlet pressure. If you can see, it's around 1400, and of course this is the flowing wellhead pressure. Okay, and ESP gasiness, we are here, so it's still good. No free gas, no free gas effect, flow curves. And let's do sensitivity analysis. Okay, let's have some sensitivity analysis on the ESP. So do we have something for ESP, artificial lift? Okay, and pump end stage. Yeah, DN, let's say 60, and then again, same thing. DN, or maybe, can I copy and paste? All right, I like that. Copy and then paste. 70, 80, 100, or 90 if you want, and then 100, 125, 150. Okay, I think that's enough. And the end. Okay, add. So I have manage sensitivity, pump and stage. So for the sensitivity one, pump and stage. Okay, and then calculate. Yep, and plot variables, sensitivity variable. Oh, it's like this. Wait. Okay, calculate. Make sure you calculate and plot variables. Sensitivity variable. Click on OK. Wait a minute. It's a bit weird. I cannot see the other. Hmm. Do we have another? Oh, can I expand? Hmm. I'm not sure what's wrong. Okay, so yeah, let's do this. Let's do this manually. Let's say 100. Okay. So my target flow rate is 3000 actually. I will use, yeah, none. So operating condition, calculate. So now with 100 stages, I move to this one, 2600. Okay, which is quite good, 2600. But to get 3000, let's change it to 125 instead. Okay, click on apply. So with 125 stages, almost there, 2900, lastly 130. Hopefully we can achieve 3000, or maybe, yeah, just to put safety factor if your pump is not in really good shape. So add more stages will help. Error. Oh, I don't expect that. I hope the software will not crash. Okay, so maybe I will exit there. So let's hopefully 130. Okay, and then okay, fine. 128. What's wrong? It's good. 126. Is it good? Oh no. So this is the best that we can achieve. Calculate again. Yeah, 2900. So maybe if you want to achieve greater flow rate, let's play with the operating frequency. Let's have 65 hertz. It's a bit greater than the normal. Normally it's 50 to 60 hertz, but let's play up to 70 hertz. So click on add operating frequency. So I will use that for the sensitivity analysis. Calculate. Okay, and then plot variables. Okay, now we have, oh, I see. So I think I put on the sensitivity stages greater than it can accommodate. So maybe that's the thing that makes when I want to show the window for the sensitivity variable plot, it didn't appear. But now it is okay. It can be done for 60, 65, 70. So yeah, let's see. Click on OK. Okay, so here. So yep. So 65 still can do. It gives us, 3,300, so it's good. 70 hertz, it's not recommended because it will give you above pump maximum. So maybe between 60 to 65 will do. Okay. All right. Just a bit. Hmm. Now it goes back to 60. So let me, what if I select it manually? Or yeah, dn, let me type in 2411. No. Okay, where are you? dn to 2400. Yeah, let me just copy here and then paste there. And let's see with 130. Okay. And then operating frequency. Oh no, pump stage. So I have sensitivity 1 and sensitivity 2. By the way, I need to click on update here. All right. And then calculate. Okay. So what happened? Let me untick this one to make sure. Okay, not. So I'm still not sure why I only have 60 here. I'm still not so sure. So if I make sure by clicking on, okay, clicking on update, or maybe I need to, yeah, like this manually. Will it do? Now. Okay, so please be careful. So I don't think WellFlo likes copy and paste. So yeah, I will do this. Or maybe let's start with, yeah, 130. So again, click on this and like this. Click on OK. Okay, like this. I like this one. Okay. Let's expand, or maybe this. So stage 130 to 973. And then, yeah, above maximum. I don't like that, above maximum. So the best thing is 130 with this 60 hertz, 130. But what about 135 instead? So 135. Can it do? Calculate. Uncheck. Yeah, this is the sensitivity. You will need this. You need to perform this if you want. Okay, now it will do. So yep, this is the flowing. This is the pump intake pressure at flowing condition. Now I can achieve liquid rate of 3000. It's even a bit greater than 3000. It's 3016 and it's stable. Good. Operating frequency at 60 hertz, and I will need 135 stages. Okay, so this will be my conclusion. So this is the available pump that I have, the N2400. I need to use 135 stages. I will need to operate my ESP at 60 hertz in order to obtain water rate or liquid rate at 3000 barrel liquid per day or barrel water per day. All right. So yeah, I think that's all. I hope this video is useful for you. I hope this video is beneficial for all of us. Thank you so much for watching and see you again on the next WellFlow videos. Thank you.